We'll start the next session soon about the multi-messenger and multi-wavelength observations of FRBs with an invited talk by Shriharsh Tendulkar. Take it away, Shriharsh.
All right. Thank you, Akshita. Hi, everyone. My name is Shriharsh, and it's a great pleasure to be here. I would really like to thank Ben and Manisha for organizing this whole thing. It's fantastic to be present in a room with everybody I have been talking to for the last 2 years and not met. So I'm going to talk about multi-wavelength and multi-messenger counterparts. That's what I was asked to talk about. And specifically, I'm going to talk about the transient counterparts. This is supposed to work. Oh, there we go. Great. So why do we care about transient counterparts? Why do we care about multi-wavelength counterparts? Well, to quote Casey from yesterday, the wise words of Jim Condon, there is nothing as useless as a radio source. And in this context, it's because radio telescopes are too sensitive. Pretty much anything in the cosmos can cause a blip which is detectable by radio telescopes on Earth. So that's why they're not very discerning. So if you want to understand the emission process, you want to have multi-wavelength and multi-messenger information. So if you can compare the energy scales of FRBs, which is about 10 to the 41, 10 to the 44 ergs, to the energy scales of GRBs, which is 10 to the 51, 10 to the 52 ergs. So that's like 9 orders of magnitude. And similar energy scales exist for ULXS and binary neutron star mergers and so on. So if you want to link all of these diverse transients together, you really need multi-wavelength counterparts. And I want to clear one thing. There are 2 different ways you can define counterparts. One is that a prompt method where you have some sort of a cosmic explosion, a GRB, a merger, or a supernova, which is this yellow star. And within a few minutes to a few hours, you'll have a FRB, which is the blue lightning. And that is what I call a prompt channel, and that's harder to find. The other possibility is that you have this sort of a cosmic explosion. You get some stable remnant, most likely a neutron star. And over years or decades, you get some sort of a FRB, maybe multiple FRBs. These are, of course, harder to associate because unless you have millisecond sort of spatial resolution saying, OK, these come exactly from the same source, the chance coincidence probabilities are really too high. So most of this talk focuses on these kinds of transients. Right. So one thing is clear, just from the observed rate of transients, right? FRBs, there are about 1,000 every day in the entire sky, which could be detectable. GRBs, we detect about 1 every day. Magnetar flares, there are about 1 every day, but they're clustered. Like if one magnetar decides to go bonkers, and it will emit 1,000 in a few weeks. But other times, it will be just completely quiet, right? Binary neutron star mergers, right now, we are detecting about 1 per year. ULX and HMXB outbursts, they're about order of 10 per year. So clearly, not all FRBs will be associated with other detectable transients. So we have to be very careful about where we put our observing resources. We have to be careful in choosing the FRBs which we want to associate. And of course, there's a problem of chance coincidence calculations. Excuse me. Oh, there we go. All right. So this talk, I've organized this talk by sort of wavelength or the messenger, going from fields where there has been a lot of work done to fields which are more speculative, and there is a lot of work to be done. And scientifically, of course, the astrophysical sources that can cause these will span a whole bunch of these different fields. So GRBs will cause X-rays, possibly optical afterglows, gravitational waves, maybe neutrinos, magnetars. Magnetars will cause X-rays, optical, and perhaps some microwave or high-frequency radio. Who knows? So first, let's talk about X-rays and gamma rays. There are a lot of different models which associate FRBs and short GRBs. Right? This is a very nice plot from Antonia Rawlinson's paper, where different phases at which FRBs might be emitted during a neutron star inspiral and merger are shown. So the merger actually happens right here, but there are a bunch of models which predict that even before the merger, say 10 seconds or 20 seconds before the merger, there could be a burst. So these are the precursor kind of models. There are models which say right at the merger, there would be an FRB. And there are models which say that there might be some sort of a metastable magnetar or hypermassive neutron star that remains. And at some point, its rotational support is not sufficient to hold it up, and it collapses into a black hole. And that is the Blitzar model, where the magnetic field of the neutron star is suddenly released, and that would cause an FRB. So this is not quite a complete list, but the reason I wanted to show you this is that there are a lot of different models. One thing I would like to point out is that before the FRBs were discovered, there were papers which thought about what sort of radio transients we might get, and the timescales they predicted were a few seconds, not few milliseconds, right? So this is going to become more important later in my talk. So the takeaway message here is that there are a lot of different models about when and how FRBs can form before, during, or after binary neutron star or neutron star black hole mergers. So we should search for them. The challenge is we might not find the FRB. It is possible that GRBs will be beamed in one direction and the FRB will be beamed in the other direction, and we might see one, but not the other. So that's one possibility. The other possibility is that most of these, after the merger especially, there's going to be a dirty environment. It's going to be a lot of plasma. So the FRB might be emitted, but it may not ever make it out to be detectable. So that's another challenge. But there have been other cases where X-rays and gamma ray counterparts have been found. One of the most beautiful ones are magnetar flares. So this is SGR 1935. I won't spend much time on this because Sergey already showed this, and this has been talked about a lot. One key thing is that we do have a very nice measurement of the X-ray and radio light curve, and we can align them very precisely. So the X-ray does come slightly after radio. But there are a lot of X-ray bursts without radio, and there are a lot of radio bursts without X-rays. So we need to understand what exactly is happening here. So these coincident detections are sort of key to understanding what the emission mechanisms are, the microphysics of the emission, but they are rare. So you have to be really looking out for them. So people have tried to do a lot of searches for GRBs at the times of FRBs. So I'm going to show a couple of them. This is work done with the student Akash Hanumarlapudi with the Astrosat CZTI detector, but there has been work done with GBM integral and other X-ray telescopes as well. And the idea here is that you have all these arrival times of fast radio bursts, and you go and ask, are there sub-threshold X-ray bursts at the times of these bursts? And it turns out most of them have non-detection. So we have fluence limits of about 10 to the minus 7 to 10 to the minus 6 ergs per square centimeter. And now with VO events, there have been more rapid response has been possible. So the Guano system, which Aaron Tohuwawohu has set up, has been able to quickly move Swift to a particular FRB location, or get photon level data from BAT for doing more sensitive analysis. The challenge here is that these limits themselves are not very constraining. But if we have a detection, that would be fantastic. So that makes it worth the search. So the aim here is to continue doing the search without getting disheartened. We can also ask the inverse question, given a GRB, can we find an FRB-like transient? And that is exactly what Alice is going to talk about very soon. So I won't spend too much time on here. Just to point out that previously this has been done with physical telescopes which are slewed around. So this is work done by Keith Bannister back in 2012, where they followed up GRBs by slewing a 12-meter telescope. So that takes a few minutes, right? But with electronic telescopes, you can actually slew the beam within seconds. So you can actually get onto the same location as the GRB much faster. If you have a repeater, of course, you don't expect it to be a GRB, but you might consider it to be a magnetar flare kind of scenario. And what you can do is focused observations with X-ray telescopes. These will obviously give you much deeper limits. So the fluence limits you can get are about 3 orders of magnitude better, 10 to the minus 10 to 10 to the minus 9 ergs per square centimeter. And at the distance of about 150 megaparsec for FRB 2018-0916B or R3, this energy limit corresponds to about 10 to the 45 ergs, okay, which is much, much higher than the typical FRB energy which you get from these repeaters. Just to put this in perspective, SGR 1806-20, which emitted an extremely powerful giant flare back in 2004, put out a total energy of about 10 to the 47 ergs. Whereas the SGR 1935 burst, which came out in 2020, put out an energy of about 10 to the 39 ergs. So we are straddling this range somewhere, but we are not able to completely constrain these kinds of bursts. So the aim here would be to find more nearby repeaters and follow them up with simultaneous X-ray and radio observations so that we can improve these constraints. Now let me switch to optical and near-infrared. Most of these efforts are for repeaters because it is really hard to randomly find FRBs in the same optical fields. So, but I will talk about that later as well. So there has been a lot of work of taking cameras which can take high frame rate observations, do photometry at high speed, and look for optical transients at the same time as radio transients. And Yuu Niino is going to talk a little bit more about that. So I won't go into too much detail here. But there have been a lot of observations which can put limits of up to 50 millijansky millisecond per burst. And if you stack all these bursts, it can get even better. So these are not constraining yet, but they could be if your FRB fluence is much higher. So if you have really bright FRBs, the ratio of optical fluence to radio fluence can become much smaller, and you can actually start constraining theories. This, of course, requires specialized high-speed cameras and large telescopes to get sufficient photons. But you might ask the question, can we do this with large area surveys? And the answer is yes. You can do this with the same kinds of telescopes which are used to search for supernovae and so on. There is the deeper, wider, faster survey, which has an amazing, very futuristic control room, I think, with lots of DS9 windows. That does a fantastic job of observing with radio, optical, infrared, and X-ray all together. And there is a very nice e-talk about these observations, which I would request you to go ahead and watch. There is also future possibilities with every scope, ZTF, Vera Rubin Observatory, and so on. The challenge here, of course, is that you have integration times of 10 to 60 seconds. And how do you separate out asteroids, satellite glints, and what have you from these single frame transients? And there's a very nice talk given today morning by Guillaume Omar about how we can do this by using atmospheric speckles. I would like to point out that the LSST science had already thought about these things back in 2011, where FRBs were barely known, that we could use LSST to do a lot of things. Actually, this was back in 2008. This was adapted from Arnero. This is like a meta level of citation. So with this, let me go ahead to gravitational waves. And this is really interesting, right? We tried putting in limits on binary neutron star-like mergers at the CHIME FRB catalog 1 arrival times. And we searched for, FRB for binary neutron star-like merger signals coming in a window between minus 600 seconds to plus 120 seconds. And the searches were done both with modeled and unmodeled forms. Now that gives us limits on how far away the neutron star mergers have to be to not be detected. So this is work done by Ryan Fisher, Eric Howell, and others in the LIGO team with some contribution from us. Future runs of LIGO will, of course, be more sensitive, and there is a higher likelihood of detections. But of course, I had to change my slides, as is the norm for FRB conferences, because there is this breaking news which shows that there is a possible association of GW 190425, which is actually a binary neutron star merger, with FRB 2019-04-25A, which happened about 2.5 hours after the gravitational wave merger happened. Now, there are some challenges in calculating exactly what the chance coincidence probability is, but this is certainly very, very interesting.
5-minute warning.
Thank you. Okay, I'm going to go a little bit faster. This is a very speculative slide. We want to find FRBs at redshift 5 or even 12, as somebody mentioned earlier in the conference. But to do that at typical observing sites, we need to understand the local FRB rate at 5 to 10 gigahertz, which we have no idea about. If the FRB rate drops above, say, 2 gigahertz, we would know about it. So one thing to consider is, can we make technological advances that make wide area searches possible at higher frequencies? Can we even go up to even higher frequencies? Let's say the South Pole Telescope and the Atacama Cosmology Telescope, can we search them for millisecond transients? They have already been searched for minute and hour timescale transients by this paper by Guns et al. So that's something to consider. Another more speculative thing are neutrinos. So there have been searches for neutrinos from FRBs, and that has drawn a blank. And they're really hard to find. And you might ask, why do we want to find neutrinos? Do we really expect them? The answer is no, it's really hard, because this is one of the expectations from Brian Metzger's papers. And you can see that the distances for these FRBs, for them to be detectable, is like 0.1 kiloparsec. So they really have to be next door. But nature has a way of surprising us. We have recently, I was very surprised to read recently that there are TeV neutrinos which are associated with tidal disruption events, which are not even very relativistic. So we don't know how they are created, but they do exist. So we don't know what will happen for FRBs. All right, so we had this discussion in the morning. I think the instrumentation session basically said all of this. We need to focus on the brightest and nearest FRBs. We need larger fields of views. We need more sensitive X-ray telescopes. And I would argue we need to be more inclusive in finding FRBs. What do I mean by being more inclusive? We should figure out whether we are seeing all the radio bursts, right? This plot keeps me awake at night sometimes, because the timescales given here are 100 milliseconds and 500 milliseconds. If this model is true, we are not going to see this. No radio telescope actually searches for these kinds of transient timescales, and we would simply miss them. So they're fairly cheap to search, so we should please search these. I would point you to a poster by my postdoc, uGMRT, where we are trying to do some work on searching these with CHIME. Similarly, as Mark pointed out in the previous talk, we also don't fully search the shortest time resolution, so we might be missing things there. So I would urge everybody that we should expand our horizons as far as possible. The last thing I want to talk about is chasms. I've improved on Liam's acronym, because there is an H which is nice. So we need to have extremely wide field of view monitors, going up to about 10,000 square degrees or even more. Stare and Grex have given fantastic value for their money. You can build a cake pan telescope and detect a galactic magnetar. That's fantastic. Every telescope has far side lobes, and we can detect things from very far away, and we should be careful not to throw those out. Veli already talked about the burst telescope, and we are considering something very similar called Astra in collaboration with Veli, but it's a slightly different design, and it's meant for external and internal triggers, which it'll have a very large voltage buffer. So come on, yeah. So this is a feed designed by one of my students. It works from 400 to 800 megahertz. And you can see that the field of view is extremely wide. It goes almost 120 degrees. That's the half power beam width. So these are the kinds of feeds which we are trying to build for an array on the ground. And I'll plug our newest X-ray telescope. This is a proposed mission which is phase 1 funded. It consists of 2 satellites which have detectors all around them in orbit around the Earth on opposite sides. And each of them has a effective area of about 1,300 square centimeters at 50 keV, with an energy coverage of 1 keV to 1 MeV. And this is built ground up for detecting transients. The name Daksha just means alert. And this will help us find gamma ray bursts and EMGW counterparts, of course. But what we are particularly interested in are magnetar flares and FRB counterparts. So with that, I will come. I should mention that effectively this corresponds to a sensitivity of swift bat, but instead of covering 1/10 of the sky, we are covering the entire sky. So it'll give us a lot more coverage for faint GRBs. And with that, I'll stop with my summary slide. There is a lot of exciting things happening. There are a lot of bespoke instrumentation projects coming online, and we already have started seeing a lot of interesting counterparts. So I'll stop here. Thank you.
We have a few online questions. Surya asks, one challenge at higher frequencies would be lack of dispersion. There's no dispersion. How to identify a burst from RFI and noise?
Yeah, so there are, that's a very good point. If you don't have dispersion, it's harder to distinguish between RFI and noise. One thing you can try to do is subtract, use two different coherently formed beams and see how the signal responds in different beams, because if you have a far field signal, it will respond differently from a near field signal. So that might be one way, but it is certainly harder.
Go ahead.
Hi, nice talk. Can you just go back to the 100 millisecond plot there? Could you maybe just explain a little bit more about where that number is coming from? I agree with you, we're probably not very sensitive.
This is a paper by Naveen and Brian, so Naveen might be able to answer that.
I see.
Yeah.
So, this number is coming from the distance that the in-spiral wind has until which the pulsar wind dominates.
So this is the interaction size scale, right?
Just to make the context clear, this is binary neutron star merger.
I see.
And as the merger happens, the pulsar wind is, or the merger wind is going to accelerate in its luminosity. So you will have an accelerating movement of your in-spiral wind, ahead of which you will have the regular pulsar wind. So up until you have this in-spiral wind, the duration of the distance up to which you have this in-spiral wind is what determines this final duration, after which you just have a solid wall. So you won't have a shock propagating this into an environment that's conducive for these environments.
I see. And it looks like from that the energy released is that energy in radio? Yes, EFRB is basically independent of the. What's the y-axis?
The x-axis is the dipole frequency, the y-axis is the Lorentz factor of
I see.
the shell that is emitted the very last moment of.
Okay. Okay, cool. Thank you. I'm just wondering whether these things are very detectable or not.
Do we have any more questions in the room? Okay, so Kiyoshi commented that SPT and ACT do read their data out at 1,000 samples per second, but they don't have a lot of spectral resolution.
Yeah, that's true. I mean, they do read it out at a very high time sampling to remove cosmic rays and things like that. But we don't have very high spectral resolution. But maybe it is not required, because since, as Surya pointed out, at those frequencies, you basically won't have any dispersion delay at all.
Zoravar, I think that has been answered on Slack. Matthew Landy is asking, I know there have been correlation studies between known FRBs and neutrinos and a search for subthreshold neutrino sources coincident with FRBs. But has the inverse study been done with ice cube neutrino multiplets and dim FRBs?
Yeah, that's a good question. I have not seen such a study of neutrinos being correlated with FRBs. But maybe I'm wrong. Maybe I've missed an archive paper somewhere.
There's also a question about when Daksha is launching. Will it put out GRB alerts in near real time?
Yeah, it will put out GRB alerts in near real time. As for the timeline for the launch, that's a bit dependent on our phase 2 funding and so on. But we are hoping that after we get our phase 2 funding, hopefully in the next few months, we can launch within 2 years or so.
Okay. I think that's all the questions. Let's thank Shriharsh again.
Thank you.
Next, we have Kelly Gourdji talking about testing a neutron star merger origin for some FRBs.
Let's share my slides. Slideshow. All right, so I trust everything's working fine. Behind this. All right, so greetings everyone from Swinburne University of Technology. So I'm sitting here remotely in Melbourne with some colleagues, Ryan and Pavan, who you heard from earlier. So we're having a little viewing party from here, although we wish we could be there in person. So yeah, today I'll be talking about two different subjects that I kind of work on day to day individually. So I'm interested in both FRBs and neutron star mergers, and in particular the radio afterglows of neutron star mergers. And so it's perhaps unsurprising that I have a particular interest in any possible connections between these two topics. And so that's the subject of this talk. How can we actually go about testing this sort of connection? Not for all FRBs, of course, we know the rates don't match up, but you know, maybe for a fraction, even a small fraction. All right, so Shriharsh showed this nice plot that was presented in Antonia and Gemma's paper in 2019. This is an adapted version. So coherent radiation in coincidence with neutron star mergers or related to neutron star mergers, the first predictions actually predate the discovery of fast radio bursts. And of course, interest has increased since the detection of or discovery of FRBs. Some of these models have been refined and new ones have appeared, such as the Blitzar model. So what I've tried to show here in this adapted version of this plot is what I think are kind of the representative categories or flavors of these neutron star merger FRB models. So starting from the far left, you have your pre-merger models. As Shriharsh explained, these are most of these models kind of have to do with the magnetospheric interactions of the inspiraling objects. Following that time scale, you have FRBs that are produced in relation to the relativistic ejecta that's launched. So as it relates to neutron star mergers, we're talking about short gamma ray bursts. And then following that, what you might be able to see really depends on the nature and stability of your merger remnant. So you might have, form an unstable magnetar that will eventually collapse into a black hole. And in the process, it might, produce a fast radio burst. And then the other models are really, you can invoke whichever magnetar FRB model you choose or whatever your favorite is. But the timescales are really going to depend, once again, on the stability and fate of your neutron star. So at the other extreme from the Blitzar model, you might end up with not everlasting, but you might end up with indefinitely stable neutron star, and we might be able to see FRBs or coherent radio emission from it for years or decades post-merger. So on this slide, I was hoping to convey what I think are some of the key, most exciting implications should we be able to ever connect neutron star mergers and FRBs. And I think there are a lot of points you could probably add to the slide, but I really wanted to look at it from a multi-messenger, multi-wavelength perspective. And so I alluded to this first point in the previous slide, is that a lot of these models really depend on, the neutron star equation of state. Ultimately, what happens when you smash two neutron stars together. So for instance, if we think about gravitational wave events, we've detected a couple of those via gravitational waves. I think 1708-17 is the natural case study, since it's the only event to date that's been where we have a multi-messenger detection. So it was detected also across the EM spectrum. So with that particular detection, just from the gravitational wave data, you have constraints on your component masses, but it doesn't tell you really anything concretely about your remnant. So, what it formed and what the fate of it was. And so I think the possibility of detecting FRBs in coincidence with neutron star mergers is could be a really interesting probe of this. The other thing I'll mention before moving on is that the relativistic jets that are launched in these systems, as well as long gamma ray bursts for that matter, are highly, they're really not well understood. So it's pretty much a mystery how these jets are launched. But some of the competing models preclude a neutron star engine. And so if you were to say see a short gamma ray burst and then later see a fast radio burst and you were able to connect the two, I think this would have really interesting implications for those who are interested in jet physics. All right, so hopefully I've advocated for why this could be a potentially interesting thing, connecting fast radio bursts to neutron star mergers, but how can we actually go about testing this connection? So as we all know, we've been, we're starting to localize FRBs, we're starting to identify their host galaxies. Is that enough to actually start, digging into this question and constraining a neutron star merger origin? And this is precisely the question that I asked myself back in 2019. So this is when the motivation for this paper was the first two localizations of one-off FRBs, and their environments were reminiscent of the environments of short gamma ray bursts or neutron star mergers. They're synonymous in this regard. And so as we have an energy estimate because we have the redshift of the host galaxy. So is this enough to actually start putting constraints on the various models I showed in the first slide? And as is perhaps unsurprising, what we quickly demonstrate is that really in order to make meaningful constraints on these various models and ultimately in order to connect neutron star mergers and FRBs, you're going to need additional information, either multi-wavelength, multi-messenger information, or even better would be all of the above. And so in this paper, we kind of demonstrate how you could use each one of these sort of added tools to constrain your models. So then the next question is, how do we actually go about building this multi-wavelength, multi-messenger joint FRB dataset? One approach you could take is to search in archival data. We saw a good example of this in one of the late breaking talks a couple of days ago by Alex Mariano. So one of the challenges, and Shriharsh touched upon this, with looking for gravitational wave counterparts to FRBs is really just the limited sensitivity of the current detectors. So they just don't see neutron star mergers far out enough. Like it doesn't probe the distances out to which we typically see fast radio bursts. And so it's my view that we're really going to probably have to wait, I would say at least, A+, if not the next generation gravitational wave detector. So we're talking about maybe 10 years before we're, able to either rule out this association confidently or start seeing, detections, which would be, of course, more exciting. I hope I'm proven wrong. I hope we can confidently connect them earlier, but yeah. So so the point of the slide was it's perhaps unsurprising for that reason that we have yet to detect in subthreshold GW searches around the times of CHIME FRBs. Like it's unsurprising that we haven't seen a detection. So I think we just have to wait a few more years for sensitivities to improve.
You have 2 minutes, Kelly.
Oh gosh, okay. So of course you can play the same game, but doing this for GRBs. So there'll be a talk about this in the next session by Alice Curtin, so I won't say more there. As has been done for gravitational waves, you can also do subthreshold searches in GRB data. So in this case, you would use Fermi, which has a wide field of view. We show an example of how you can go deeper if you have a location for an FRB. This is depicted on the slide. And then beyond that, of course, you might not always expect a GRB. You might not have it might be an off-axis event, but we might be able to see the radio afterglow. So this is the synchrotron afterglow caused by the relativistic ejecta shocking the median. And so forthcoming surveys could be interesting prospects for this. And of course, for similar reasons, you can look for optical transients. You can look for kilonova emission. So a totally different approach to searching from in archival data would be a proactive approach. So you could say, given that I've just seen a gamma ray burst, or given that I've just seen a gravitational wave event, I know a merger event has just happened. Let me trigger my radio telescope to see if I catch any coherent radio emission. And so time is of the essence for this. You need electronically steered telescopes. This is why LOFAR and the MWA are prime tools for this and have been active in this sort of studies. As you can see, our LOFAR observations are probing this X-ray plateau. And the idea here is that this X-ray plateau is caused by energy injection. And the hypothesis we're testing here is that that energy injection can be coming from a magnetar, a newborn magnetar. And so we're testing whether or not we can test its presence via any radio emission. We can play the same game, but trigger on gravitational wave events. The difference here is that GW events are have much worse localizations. LOFAR has a large field of view, somewhat counteracts that as is shown here. But yeah, so 03 we weren't able to use it in our triggers because there were no interesting events in the Northern Hemisphere that met our triggering criteria, but look out for 04, which is due to commence in March. And then, yeah, these are my last couple of slides. So I've been advocating this whole talk for joint multi-messenger, multi-wavelength data sets, but there's actually one flavor of model, the pre-merger models, where you might be able to rule them out or find a connection using the FRB alone, and you don't even have to localize your FRB. And this is because your energy reservoir for these models are strictly dependent on the orbital separation of your InspireLink components. And so we know this very well analytically. Those are those black lines. And so you can compare them directly to see if they match with the profile, with the rise time of your FRB. And using this method, we were able to rule out at pretty high confidence these two enough FRBs shown here. And then my last slide, I'm sorry that I'm going a little bit over. So you can actually do this in a more sophisticated way. This is a plot from the paper that's been submitted by Alex Cooper, as a PhD student finishing up at the University of Amsterdam. And basically he's shown is you can actually, model or predict various different light curves for different kind of parameters that you invoke in this model. And so you can imagine a large sample of FRBs at high time resolution. So we're talking about sub-millisecond levels. You might be able to actually start doing like template matching. And I think that's quite a fun thing to look forward to. So I'll end there because I know I'm a bit over, and I'll just leave my summary slide up.
In-room questions?
Hi, Kelly. That was a really nice talk. So maybe I missed this, but is there does LOFAR have a transient buffer which it can dump so that it can get time before the gravitational wave merger as well? And the other question I had was, there are these low latency or negative latency triggers which are coming up with LIGO. Do you plan to use those?
Yeah, so those are both good questions. So LOFAR's buffer is only like 5 seconds or something like that. So it's not really, buying us enough time, considering the fact that it takes us currently like a few minutes to get on source. We're not quite as fast as the NWA. So buying those extra 5 seconds aren't really, that interesting. But I would say talk to Yuri Van Leeuwen or Ines, who could probably tell you about a fun way that you can still make use of the buffer. We're hoping that the response time, the LOFAR response time will improve with LOFAR 2.0, which is the upgrade. I've shown that here on my summary slide. And then your other question about the negative latency triggers, I'm not sure that they're going to be, like, they sound good. I'm not sure that I would use them just because those triggers are quite valuable. We don't have an infinite amount of triggers, and I'm not sure how reliable those negative latency triggers will be. I want to make sure that I'm triggering on a high confidence event.
Right. Thank you.
One more question.
Hi, Kelly. Naveen here. Have you managed to point any radio telescopes during the break of the X-ray plateau following a GRB? And if so, did you manage to observe any radio pulses from that time?
I missed the beginning of your question. Are you asking if we've observed during these X-ray plateaus?
Yeah, so my question was if any radio telescopes were pointed at GRB afterglow X-ray plateau moment in order to rule out or confirm the imploding magnetar scenario.
Yeah, so I mean, we have like several data sets. So I mean, I showed an example of that where we were on source with LOFAR. I don't know if I can go back. Yeah, we were on source with LOFAR during this plateau phase. You can see here there isn't that steep drop off. So I don't know if you would want to interpret that as like the collapse into a black hole, but I think there are some examples. This paper, this MWA paper that's cited here, you might want to check that out to see which ones they were able to cover. I'm not sure if there's an example of a steep cutoff. No, I mean, if I had radio emission, I probably would have led with that. But I will say that again, with LOFAR 2.0, we'll be able to do both interferometric observations, which is what we're limited to now, which is suboptimal if you're looking for FRBs, but we'll also be able to observe at the same time, at high time resolution, which is really what you want when you're looking for FRBs. And so I think the future is promising for setting, I think, deep constraints on these sort of models.
Okay, thank you.
Thanks again, Kelly. Next, we have James Chibueze, who'll be talking about a MeerKAT, e-MERLIN, H.E.S.S, and Swift search for persistent and transient emission associated with FRBs.
Thank you. Good day, everyone. My name is James. In the last 3 days, I've heard so much about FRBs that I feel more comfortable to talk to you about multi-wavelength study that we've done recently on 3 FRBs that have been localized with the ASCAP telescope. So I'll show you some results using MeerKAT and e-MERLIN follow-up. e-MERLIN is the UK VLBI network. And then H.E.S.S telescope, which is high energy observation instrument in Namibia, as well as the Swift telescope, which does X-ray and UV observations. I would like to acknowledge all the collaborators. This is the work done in collaboration with Manisha, Ben, who's here, and the H.E.S.S collaboration. So why should we look for persistent radio emission associated with FRBs? From all I have listened in the talks in the past 3 days, I think you do need to find emissions that are associated with FRBs to be able to constrain the origin of FRBs. At least it will give you numerous information, like if you have the radio spectrum information, you'll be able to tell the nature of the host galaxy. It could also help with classifying FRBs. At least you can tell those that are associated with persistent emission, this is what they do. Those that don't, this is their properties. And you can also subclassify the ones with persistent emission. Of course, this could provide us additional questions that you would need to answer. So I would like to focus attention on 3 FRBs. Of course, I've listed a few FRBs that we know that have persistent emission, and there are others which I haven't put down here. So the observations I will show you today was done with MeerKAT at L-band and in 4,000 channel mode, which allows you a bandwidth of about 856 megahertz, and the center frequency is around 1.28 gigahertz. I'll also show you some results from e-MERLIN, which is only a follow-up to one of the detections that we had in this observation. And just to introduce the project, this is a project to look for persistent emission with MeerKAT and do follow-up observations if need be. And I'm reporting the result of the first year. We do have additional observations for a second year, and we have submitted a proposal for a third year. Why are we keen to look at the high energy component of FRBs? I've seen this in one of the previous slides, presentations. Here, Murasesan actually proposed that you could find high energy gamma ray flashes if you have neutron star or white dwarf system that produces highly relativistic magnetic outflow. So the question is it possible for us to find or detect this with the H.E.S.S telescope? Well, their paper proposed that you could detect them with H.E.S.S if the object is around 10 to 100 megaparsecs away. But you will need CTA if you are looking at objects 100 megaparsecs to 1 gigaparsec away. So we decided to give it a try. We put in proposal to do this observation with H.E.S.S. Okay. So with the H.E.S.S observation, we chose a configuration that will allow us a resolution of around 0.12 degree. This is very good for point source observations. And then with the Swift telescope, we looked at the UV and also the X-ray observations, X-ray bands. Why is this? Okay. So the three FRBs we selected for the first year was FRB 171019 and FRB 190711 and FRB 190714. I found this information about the FRBs from the FRB catalog. I found none about the third one, which is actually a once-off FRB. The rest are, the other two are repeaters. Okay. So I'll go straight to the results from FRB 171019. In this, in the case of this FRB, we had all the three observations with MeerKAT, H.E.S.S, and Swift. And that is the MeerKAT image. MeerKAT has a very excellent sensitivity. You could go down to 4 microjansky per beam, and you can see it's quite nice and beautiful image with a few radio galaxies that some of my MSc students are giving attention to. The position of the FRB, localized FRB, is right there. And if you zoom in, this seems not to be working. Then there is no detection. So this looks like it's something I was never used to as a VLBI person. You point your telescope, you get huge amount of data, and you find nothing. But apparently, I realized from this community, it is something you see all the time. Spend hours processing terabytes of data, and then you get no detection. But the good news is, you could at least give a limit, an upper limit, to whatever the radio emission from the source could be. And in this case, we put a very good limit of about 15 microjansky per beam, which is quite good.
You have 2 minutes, James.
Okay. And that is the image from H.E.S.S. Again, there was no detection, and then we could put the upper limit of the high energy gamma ray flux to 1.7 times 10 to the power minus 12x per square kilometers per second. Square centimeters, sorry. And then you could look at also the NS, seems this is not working. And that's the UV flux limit, which we got from the Swift telescope as well as the XRT telescope. At least we can confirm that the XRT is working well by the detection of a wolf star in the X-ray band. So the system is functioning well. It's just that we did not detect anything around the FRB position. So it's all bad news if you're processing the data, but it's good news for the theorists. So you can go ahead, pick up the upper limits, and go swim with it. Let's go to the next source. So this is the next one, FRB 190711, where we have only MeerKAT observation, and again, no detection after hours of processing terabytes of MeerKAT data. But again, we can put the upper limit to 15, something less than 15 microjansky per beam. Yes. And then we'll go to the interesting one, I think, which is FRB 190714. There is not much information on this source, but we do have MeerKAT, we have e-MERLIN observation, and pan-stars. So here we at least detect the FRB in MeerKAT. The background you see there is a MeerKAT image. The star is the position of the FRB. The 2 circles are the position of the 2 sources we detected with e-MERLIN. The black contour represents the optical pan-star image. At least there is one good news, 1 out of 3, 30%, which is nice and encouraging. Our observations, of course, included searching for the FRBs using the MEerTrap backend. We detected no pulses, but we found new persistent emission towards this object. And in each of the sources, we had 2 epochs of observation with MeerKAT, and in the case of this source, we detected the persistent emission in both epochs. Can you go to the next slide? Okay, so in the second epoch, we also have a detection. If you go to the next slide, that is a nice zoom-in image to show all the things we have. Okay. Next. Okay, so the table here presents the information we got from both the e-MERLIN, which is the VLBI observation to check whether the emission is compact or not compact, and also the MeerKAT observation. But we still could not answer the question, is the persistent emission compact? Well, we do have 2 sources from the e-MERLIN. If you understand what is tapering, which is flagging your long baseline and then convolving your data again, you find some extended emission which represents the southern source, which I showed in the object. So the northern source was detected with the highest resolution. So if you decay your resolution a bit, you will detect the southern source. So there are 2 sources. We're not sure which one is associated with the FRB, if any. And also the source is very much in the southern hemisphere. So the beam of the e-MERLIN, which is in the north, is quite elongated. So it's quite difficult to constrain whether this is really a compact source. We have put in proposal with the H.E.S.S, the high sensitivity array. I'll show that in the next slide. The other question here is also that we don't have information about the spectral index. We don't have enough sensitivity to compute the spectral index of the source, so we can't tell you if it is synchrotron or if it has anything to do with Bremsstrahlung emission, but this could be done in the future results. Next, please. So we've searched for persistent emission towards 3 FRBs. We detected 1, we didn't detect in the other 2. And the persistent emission we detected is still not constrained as to whether it is compact or not. So we have additional proposals with the H.E.S.S and the EVN, which we accepted to do this observation. So there will be more results coming. And then the observations for the year 2, both with the with MeerKAT, H.E.S.S, and Swift are all completed now. We're handling the data, so there will be more results. And the proposal for this year 3 is in. Hopefully it comes with a positive result, and we will have more results. Thank you.
We have time for a quick question.
Yeah, thank you very much. This is so exciting. I have a couple of questions. So the first question is, so the VLBI position is not for the FRB. Instead, it is for the persistent radio emission, right?
Yes, those 2 are the VLBI positions from e-MERLIN.
Right, so you still do not have a localized position for the FRB, right?
This is the localized position for the FRB
the star
from ASCAP.
Oh, okay.
So all the 3 FRBs we're looking at have localized position from ASCAP observations.
And these PRSs are within the error bars, like
yes.
Of that. Okay. Yeah, that's interesting. Then the other thing I wanted to clarify, so when you talk about compact, you're trying to get the compactness of the source. Is it the same as finding out if it's unresolved or extended? Okay,
so if you go to your visibility plane, pick out the visibility of your source, and then you plot the visibility amplitude against the UV distance. This would decay, okay, based on your baseline until you fully resolve the source, then it flattens. So if it flattens, then that object is fully compact to your array. So we can't confirm whether this is compact because now we're seeing two sources in this object, and we also cannot fully associate any of the two with the FRB yet. So,
okay, so I think my question is it a different context? So when you talk about compactness and being resolved or unresolved, are they different type of things?
Compactness and being resolved or unresolved. So with...
We are running out of time a little bit. Maybe you can continue your chat later. Yeah.
I think, yeah, it's better to have a chat offline.
Let's thank James again. Next up, Suryarao Bethapudi talking about observing R3 with uGMRT and Effelsberg.
So hello everyone, I'm Surya. I will be sharing some results about FRB2022-916B with Effelsberg and uGMRT. This work is done as part of the GMRT Effelsberg FRB collaboration, and this is a collaboration I want to give a huge thanks to everyone there because they're all supportive and all, they help me a lot. So what do we know about this FRB? So this is also known as, lovely known as R3. It has a 16-day period with a 2-day active window at 600 megahertz. And I would like to highlight the 600 megahertz because it is chromaticity. And it has been already been established by Planius 21 and Pastor Marizuela 21. And we also don't know what causes this FRB. There's binary models, magnetar models, and of course jet precision models. So what we're going to do is that we will take a burst sample, which consisting of bursts, and every burst will have a phase. Since it's a periodic FRB, we sort of map every MJD of the burst to a phase, and then we can also get the center frequency of the burst. So let's just put them in the frequency phase diagram and then just highlight the instrument bandwidth also. The first one is the CHIME FRB sample, and then we'll add the apparative sample over it, and that's in green, and then the LOFAR sample, and we can straight away see something happening here that they are not aligned perfectly with the 0.5 line, which is denoted by the broken dotted blue line. So, okay, now this is there. If we see something like this, the next step will be to actually fit a power loss to it. So we actually fit 2 power loss to it, the peak phase, which is denoted by the dark black line, and the full width at half maximum window, which is the gray shaded region. So once we did that, if you want to test this, we basically have to go to a frequency regime where we don't have any bursts. Since we can't go below 100 megahertz, we have to go above 1 L band. So we go to 4 to 8 gigahertz, which is denoted by the blue line. So this is where enters Effelsberg, because Effelsberg has a CX receiver with the linear feeds, which operates between 4 to 8 gigahertz. So we did 2 campaigns with this. The first campaign was done over the entire period. So basically every day of the period for 1-2 hours, and we did not detect any burst. And the second campaign was targeted. Since we have a chromaticity model, basically a peak phase and a full width of half maxima versus frequency, we can design windows such as a window starting at 7 gigahertz and stopping at 5 gigahertz, and windows from peak at 7 gigahertz to a peak at 5 gigahertz. Those are denoted by the shaded regions, shaded orange regions. So once we basically give these limits to the scheduler, and the scheduler schedules them, we basically do observations, which are denoted by the bold black lines, and then we sort of detected bursts, which are denoted by the green dashes. So if you put those bursts again on this plot, we see that they are clustered around right near the peak phase, the black bold line. So this is the burst sample that we get, and one straightaway feature is that all of them are narrow. They are extremely 1-2 samples wide and high, and width, so it's kind of hard to do. But there's one sample, which is one burst, which has had Tromon structure, which is we are all very familiar with, and it has almost flat position angle and high linear polarization fraction. So if we take our sample and basically put it on the bandwidth versus on this plane, we basically see that the bursts at higher frequencies are narrower and have larger bandwidths, and bursts at lower frequencies are wider in time and have lower bandwidths. And also, if we sort of compute the fractional bandwidth, which is also nothing but a ratio, then we see that it's not constant. And this is also interesting because it has implications for magnification, plasma lensing and stuff. Moving on to go to the models. So we will only be discussing the models which post-date chromaticity because it's really unfair to discuss models after chromaticity was discovered. So there's the binary models. There's a binary comb in which a binary neutron star is in a companion with another compact object with wind. And the occultation with the wind causes periodicity. Chromaticity can be explained with free absorption and sensitivity arguments. So there is really not much else to say about this without going into the nitty-gritties. And so we basically move on to the BE-type star magneta. And this is also a neutron star orbit with a BE-type star which has wind or a disk. And the bursts happen when the neutron star's inside the disk because like something happens, neutron star interacts with the wind and it has star quakes and stuff. And the chromaticity is explained due to free absorption. But since the bursts happen when the neutron star is in the wind, and due to the free absorption and stuff, there's a prediction here that the bursts will, at multiple frequencies, start at different times, but they end at the same time. But this is sort of kind of like a contradiction to us because we see bursts at L band and higher frequencies start at different times and end at different times than the lower frequency parts. So this is kind of like not sure. Moving on to magneta models, which is basically largely work done by Dongzi. The main hallmark feature of these models is that there is a magnetic axis offset. So if you have a magnetic axis which is sort of like a diameter, then you are bound to get broadband emissions like regular pulsars and magnetars. So really can't expect repeating FRBs to come from there because they are narrow in bandwidth. And also synchrotron emission because there's a magnetic field there. So really, to understand these kind of models, there's a tool called the PA phase, which is basically you sort of have the PAs on the x-axis, y-axis, and the phase on the x-axis. So basically, we'll only discuss two magneta models because the force position is kind of like already been shut down. The slow rotating is where we discussed in the last session, where the spin period is the FRB period, and the precision period, and the free precision is where the precision period is the FRB period. So moving on, so this is what I mean by PA phase, where the PA is plotted on the y-axis and the phase on the x-axis. So this is, these are all the bursts detected by Effelsberg at 5 gigahertz. So we can see that there's some clustering happening here, that the bursts which are nearby in phase have similar PA values, but there's one burst which occurs around 7 hours later and has extremely different PA values. So, but since there's only one burst, so we are really not sure if we should, consider that. So if I put all the other bursts that are there which have some public PA values, then we get something like this. The apertive sample is at L band, and it's colored in purple, and the GPT sample at 800 megahertz in colored in orange. So we see that there's some clear structure here, but the green point of our data set is sort of an oddball here, that is a different phase. But there's a caveat here that we can't actually do a comparison here because not all of them are absolutely calibrated. So what do we need? So we need more bursts to fill in the PA phase diagram. And for that, we need a sensitive instrument with a long integration so that we get more bursts. And in the bandwidth of 500 to 700 megahertz, because that's where the party is, because there are a lot of bursts there. And maybe also large bandwidth, because large bandwidth is always helping. And also with polarization calibration capability. So this is where uGMRT enters. So we did a 36-hour campaign. We detected around 83 full Stokes bursts. And of them all, so this sample is probably comparable with the CHIME sample. And we have two bursts which are sort of like interesting. And by interesting, I mean that if GMRT consists of 27 antennas, and you can basically take half of them to point it to work in L band and the other half to point at different frequency band. And doing so, you basically have a large frequency coverage in a simultaneous fashion. So the burst to the left has the desired trombone structure that starts in the band 5, and then it sort of disappears at the edge of the band, and then it suddenly miraculously appears again at the lower edge of the band. And the burst to the right has, again, desired trombone structure, but this time it actually continues. And we see that it continues all the way to low frequency edge.
You have 2 minutes, Surya.
Yeah. So a thing here that I should have mentioned is that we have basically taken both the snippets and we dispersed them to the same reference frequency of 1200 megahertz, which is the top edge of the band 5. And we discovered two such things in a 6-hour observation. And So currently we are only able to do polarization calibration with the band 4 because I've been slow with the analysis. The work is still in progress, so I just want to flash some polarization calibrated RM fitted bursts, which is the band 4, it's just like sort of like the really nice band at uGMRT. And we see a lot of different morphology and flat PA structures and high linear polarization and a very nice, interesting structure. And the summary slide is that we have seen chromaticity until 5 gigahertz, so we have burst at 5 gigahertz. And we are still analyzing the GMRT burst sample, still measuring RM, so watch out to paper soon, and Gamsamida.
In-room questions? I had a question about whether you can comment something about the scintillation bandwidths you measure at Effelsberg.
Yeah. So, excuse me, can I get the slides back? Yeah. So we basically, we can measure scintillation bandwidth at these frequencies because it's around 1 to 3 gigahertz based on the frequency scaling. And since we are at high frequencies and the scintillation is happening inside the Milky Way, and due to the motion of the Earth, we at higher frequencies we see a new part of the scattering screen, and that's why our scintillation bandwidths sort of change with time. And the time scale of this change is around 1 period at these frequencies. But if you go to lower frequencies like L band, it takes more than a year for the scintillation bandwidth to change. So does that answer your question?
Yeah, it does. So you associated this change with a screen in the Milky Way?
Yeah, screen in the Milky Way, yeah.
Thanks.
Yep.
Suryarao, can you comment on the changes in the burst drift rate, if you do see any, between bursts arriving at different phases of your active phase window?
So there's, by drift rate, do you mean the one in the side-Roman structure, or do you mean? So there's only one burst there, so it's, I didn't do any calculation because, firstly, because we are not time resolved completely, so there is structure there, so it's not at low time resolution, so I didn't bother much with it. But we're doing another survey at higher time resolution, so probably we'll be lucky there and get more bursts, and then I can probably answer your question.
Okay, thank you.
Yep.
Let's thank Surya again. Next up, we have Yuu Niino giving a remote talk.
Okay, I hope you can hear me well. I'm Yuu Niino from the University of Tokyo. Today, I'd like to talk about the high-speed optical observation of a repeating FRB using optical facility named Tomo-e Gozen. The observation was conducted in collaboration with the people from both the Tomo-e Gozen team and FAST team. Okay, so other wavelength counterpart is an important clue to understand the nature of mysterious transient, and so we are various search for counterparts are conducted in various wavelengths and in various time scales, as we have already seen. But in this talk, I'd like to focus on the optical counterpart in a short time scale, prompt optical flash, in other words. And we don't know such emission exists or not yet, but there are some hints. The galactic magnetoburst had an X-ray counterpart that demonstrates higher energy counterpart, short time scale counterpart is possible in a FRB like emission. And speaking of optical emissions, there are some traditionally known radio pulsars that is also detected in optical. And there is also some theoretical models that predicts possibly detectable optical emission in a short time scale. So we'd like to find these emissions in reality. So actually, the short time scale observation in optical is quite challenging because most of the existing optical facilities uses CCD sensors that takes at least a few seconds to take data once. But there are some high-speed facilities on Earth, and actually there have been some observation FRB sources using those facilities. Currently published results are mostly targeting R1 FRB 121102. In Hardy et al., they used ultra spec camera mounted on Thai National Telescope and obtained 90 millisecond timescale limit. And there are also observations using observation by magic corporation. They use their Cherenkov gamma ray telescope as an optical facility, and you obtained 1 millisecond timescale or shorter limits. However, there are many other repeating FRB sources unexplored in with optical facilities. So we conduct further observations using the Tomo-e Gozen camera mounted on the Kiso Schmidt telescope. This is the image of the camera. This facility is mounted in the cylinder of the 1 meter Schmidt telescope in Japan. And this camera has uses CMOS sensors, 84 sensors, and had 20 square degree field of view in total. And it can read the full frame, full field of view with 2 FPS frame rate, and faster, higher frame rate is possible with partial readout. Okay, using the Tomo-e Gozen, we have conducted the same time observation of repeating FRB 190520b as an outlier event of the macro relation. And in this observation, we used the partial readout mode with which we achieved 24.4 frame per second frame rate. Even with this partial readout mode, we have 8 times 5 arc minutes field of view per each sensor, so we can easily have the target and calibration star in a same field of view. And with that frame rate, the exposure time per frame is 40.9 milliseconds, and time gap between the frames is only about 0.1 milliseconds. So generally, we don't need to worry about the loss of signal in the time gap. We don't use any filter, and the observing passband is around 4,000 to 7,000, also in the middle of the optical passband. Okay, the simultaneous observation was conducted in August 2020, and 11 radio bursts were detected by FAST during the simultaneous observation with fluence range of 60 to 300 millijansky millisecond. And we didn't detect any optical persistent object like host galaxy in our stacked image, but we conducted a forced photometry of the FRB coordinate to see any short signal available. This is obtained light curve, and the observing condition was not good on day 1 and day 4, but there were any radio bursts on those days. And in day 2 and day 3, we had a good observing condition, and all 11 bursts occurred on those days. And we don't see any excess of optical flux associated with radio arrival times. These vertical dashed lines are the dispersion measure collected radio burst arrival times, and we don't see any optical flux associated to them. Zooming into the arrival times of radio bursts, again, we don't see any excess in optical. The obtained optical flux is always consistent with being 0. So with these data, we compute the optical upper limits on the optical emission from these bursts, which is shown in this figure as a function of corresponding radio fluence. The limits for individual bursts ranges from 0.07 to 0.4 Jansky millisecond after collected for the foreground extinction in the Milky Way. These two data points, sets of data points collected with that dotted line is collected the limits with extinction collection and without collection. So as we know, the FRB, this repeating FRB is an extragalactic source. So we basically see the extinction collected value. And after stacking all 11 frames that correspond to the arrival times of radio bursts, we obtain upper limit of 0.3 Jansky millisecond. This one. And collecting corresponding radio optical to radio frequency ratio is about 0.2 to 2.1. In the figure, we have also shown the previous results by MAGIC and Autospec on R1 after collection for the foreground extinction. And so our stacked limit is a factor of a few better than previous results, although the corresponding radio frequency is larger for these events. So in terms of the radio to optical frequency ratio, actually that is what we want to know in order to understand the emission of FRBs. Our limit is somewhat similar to the previous results because our limit in optical frequency is deeper, but their radio frequency is larger. So in terms of ratio, the limit comes to this similar place, and it is comparable to the SED of club pulsar. That is quite bright in optical, but we didn't get anything. So typical optical to radio ratio of FRBs would be smaller. But
2 minutes.
Okay, but yeah, we have good limit in fluence. So if we detect, if we put the similar limit simultaneously with brighter radio bursts, we can go deeper. If we detect the same limit with the 10 Jansky millisecond radio burst, can lead to SED of Geminger. And if we the same optical limit with 100 Jansky millisecond radio burst will lead the here. That is interpolation of the radio and X-ray emission of the magnetoburst. So we are putting the first step in the interesting parameter range, and we can possibly go deeper in the near future. So to make it realize, we are conducting further observation using a new facility that is a PRIX mounted over 3.8 meter larger telescope and can achieve 98 FPS with three bands at once. And while PRIX is monitoring the repeaters, Tomo-e Gozen is also conducting a wide field survey. Actually, as I mentioned earlier, the Tomo-e Gozen has total field of view of 20 square degrees, so it is a very wide field facility without partial readout. So we observe the field of view of Chang, and the overlapping field of view is about 5 square degrees. So the expected event rate is not very high, but the effort is ongoing. So please stay tuned. Okay, this is the end of my talk.
Questions?
Really great talk. I'm wondering if you had to worry about the stray light from the nearby star contaminating your fluence measurement in optical?
Well, I think that is okay, and our background is quite flat.
Okay, cool, thanks.
Any more questions? Then let's thank our speaker again. Brings us to the end of this session. And I think we'll be starting the next session 10 minutes later, so at 3:25.